Hello students. Uh, so in our previous lectures, we have seen a lot of topics related to kinetic theory of matter, and we have covered many topics. We have defined the postulates of kinetic theory of matter. We have then defined the kinetic theory of gases also. We have seen different states of matter. We have seen we derived the expression for pressure inserted by a gas. But actually, we have just studied the physics in terms of theory only. But to understand physics, it is important to apply the laws of physics to the numerical problems. Okay, so today's lecture and the next lecture will be focused on different topics, but in terms of the numerical problems based on these studied topics. So today I will consider some of the topics which I have already discussed in my previous lectures. We will of course recall all the laws which we have discussed in our previous topic, and then we will see how to solve some numerical problems based on these laws. Okay, so today's lecture objective, if we look onto this, the objective is to acquire the understanding about the implementation of concepts related to the kinetic theory of gases. We have divided it into two parts. And the outcome of today's lecture will be, after attending this lecture, you will be able to solve the practical problems based on the principles studied so far. Here are the reference books. Again, the same books I have considered, and you can also go through these books to understand these principles, these laws, or the numerical problems based on these laws. Okay, so on the basis to acquire the objective of today's lecture, I have divided this lecture into two parts. One is we will recall all the laws we have studied so far. Actually, the laws also I have divided into two parts. I have just focused, today I will focus only the laws related to kinetic theory of matter. Okay, we will consider different, like for example here kinetic energy, we will consider the gas equation, we will consider the Boyle's law, Charles law, Reynolds law, and some other topics. The rest of the topic, for example, the van der Waals equation of a state and their corrections, and the transport phenomena of the gases will be considered in the next lecture for their numerical problem. So let us start with the recall of different things we have studied in the previous lecture. The first one was, what is the expression for the pressure that is exerted by a gas? So we have already derived it. We considered one three-dimensional box, cubic box, and then we considered only one particle first that was striking on one wall, and then striking on the second wall, and then we have considered the momentum, total momentum, and according to that, the change in momentum in one direction we have calculated, and finally we have calculated for all the three directions, all the possible directions, and finally we calculated it for all the molecules in the gas, and the formula came up: P is equal to mnc square upon 3v. Okay, where small m is the mass of one molecule, n is the number of one molecule, and C is average RMS velocity of the gas molecules, and V is the total volume. So this we can write, because we are seeing here m into n is nothing but the total mass of gas. So we change this m into n into capital M into C square upon 3V. And if you see here, m is the mass of total gas and V is the volume of total gas. So m upon V can be written as the density of the gas, and that is converted to P equals to rho into C square upon 3. Okay, where rho is the density and C is the RMS average velocity of the gas molecules. Okay, then second formula we have seen the kinetic energy of the molecules. So kinetic energy is given by, we know this is quite general expression, 1 by 2 m into C square, means mass into velocity square, divided by half. The another expression for the kinetic energy is given by Boltzmann law, and that is given by 3 by 2 K into T. So where K is Boltzmann constant and T is the absolute temperature. So we can write it together that 1 by 2 mc square is equals to 3 by 2 K into T. The next thing we have studied was gas equation. We have derived this gas equation from the expression of the pressure exerted by gas. Okay, and the final equation is well-known equation. Everyone knows this equation. PV equals to RT, where P is the pressure, V is the volume, R is gas constant, and T is the temperature. Okay, then there are some other laws which also satisfy ideal gas condition. Okay, these are given only for the ideal gas law. Of course, we can modify these laws for the real gas condition, because there is a huge difference between the ideal gas and real gas. Okay, anyway, we will consider first for the ideal gas, and you can see here the first law is Boyle's law, that is PV equals to constant, and the condition is for the condition for Boyle's law is that should be at constant temperature. Okay, then the second law we introduced was Regnault's law, and that is given by P is directly proportional to the temperature. That means the pressure of gas is directly proportional to the temperature if the condition is volume should remain constant. That is second law and known as Regnault's law, right? The third one is also very famous law and known as Charles law. So what Charles has told, the volume of any system should be proportional to temperature, or we can state in the sentence form that volume of gas is directly proportional to temperature provided the pressure of system remains constant. Okay, so these are three important laws, and we will see how to implement them for the thermodynamic problems. Okay, then we will see Avogadro hypothesis, the next topic which we studied about the Avogadro hypothesis, and it tells us about the number of molecules are equal if or we can state in the sentence form, in the mathematical form, is just the number of molecules are equal of the two gases if the equal volume of the two gases under similar conditions of what? One is temperature and pressure. So if two gases have same temperature and pressure, the similar volume should have the equal number of molecules for both gases. Okay, that was known as Avogadro hypothesis. The next relation was Graham's law of diffusion of gases. So that was written mathematically, R1 upon R2 equals to C1 upon C2 equals to under root of rho 2 upon rho 1. That means R is the diffusion rate, C is RMS velocity, and rho is the density. 1 and 2 is respectively for gas 1 and gas 2. Okay, now according to this relation we can say that the diffusion rate is directly proportional to the RMS velocity of the gas molecules, and both of them are inversely proportional to the density, under root of density of the gas. Okay, that is the relation given by Graham. Okay, the next relation is about Maxwell's law of equipartition of energy, which states that the energy associated with each degree of freedom, either it is translatory motion or it is due to rotatory motion, the energy associated with each degree is given by 1 by 2 into kT, where K is Boltzmann constant and T is the temperature. Mathematically, we can write, because if we consider one molecule or one particle in 3 dimensions, there can be 3 different there can be 3 degree of freedom associated with this molecule's motion. Okay, so for that we can consider the velocity component in each direction that is given by, we have considered it as u, v and w in x, y and z direction. So the energy for this particle or for this molecule can be written by 1 by 2 m into u square. You know, for ideal gas condition, the energy is solely equal to kinetic energy. There should be no potential energy because there is no interaction between the molecules. So that's why only kinetic energy matters here, and that is given by 1 by 2 m square in x component, 1 by 2 mv square that is in y component, and 1 by 2 mw square that is in z direction. So all of them are equal to 1 by 2 into kT, right? So this is Maxwell's law of equipartition of energy. The next was, we have studied about the degrees of freedom, the total number of independent variables, that is known as degree of freedom, and we have established a relation between molar specific heats of gas and the degrees of freedom, and that was given by gamma equals to Cp upon Cv. Gamma is the ratio of molar specific heat at pressure and molar specific heat at constant volume. So that is Cp upon Cv is given by 1 plus 2 upon F, where F is the degree of freedom for that particular gas molecule. Okay, then we have derived 3 different equations that were given for adiabatic expansion of ideal gas. So what is the adiabatic expansion? The expansion in which no heat is exchanged between the system and its surroundings. So these two are independent of each other. There is no energy transfer between the system and surroundings. So for that we have calculated, we have derived 3 different equations that gives the relation between 3 different variables, that is temperature, volume and pressure. The first relation was T into V to the power gamma minus 1 equals to constant. T is the temperature, V is the volume and gamma is the ratio of specific heats. Okay, the next relation was obtained by putting the value of T from the ideal gas equation, PV equals to RT. So T is equals to PV upon R, and from there we have got this constant term P into V to the power gamma equals to constant. This is our second relation which relates pressure and volume for the adiabatic expansion. The third relation relates the 2 variables that are pressure and temperature, and that can again be obtained from these equations by putting the value of respective term. Here now volume is not there, so we can replace volume in this equation and we can get P to the power gamma minus 1 divided by T to the power gamma is equal to constant. So these 3 are very important equations which are given for the adiabatic expansion of ideal gas. This all was related to the ideal gas conditions. But now when we consider the practical gases, the real gases such as oxygen, helium, nitrogen, Similarly, the other gases are also real gases. For that, there must be some deviation in all these studied laws, and that was observed in the experimental condition, that was observed by different scientists, and it was needed to modify the ideal gas laws or ideal gas equations, and according to that they have provided some empirical law that is known as modified Boyle's law for real gas, and the equation was given by PV equals to A plus BP plus Cp square plus dP cube plus so on, where A, B, C or D are known as Virial coefficient, and the values of these were in the order of A is greater than B, that is greater than C is greater than D. So in terms of their magnitude, the order was something like this. If we consider the low pressure condition, that means, if we consider the low pressure, that means P tends to 0, and if P tends to 0, that all the terms will be 0, and what will be remaining? PV equals to A, where A equals to RT, and that means this changed to the Boyle's law. Okay, the Boyle's law was PV equals to constant. So we can consider this also, because at low pressure the real gas also behave like ideal gas, because the interaction between them or the intermolecular forces between the molecules of these gases is quite low, and that means there is no interaction or negligible interaction, and that means it behave as a ideal gas. So that's why the real gas at low pressure behave as ideal gas and simply follow Boyle's law. Okay, that is given by PV equals to const. Right now, one more term was defined, that was Boyle's temperature. What was that? This is the temperature at which the coefficient B become 0. Actually, the value of B in this equation is very important. At the temperature where this term becomes 0 is known as Boyle's temperature, and that is given by TB. Okay, normally we write the absolute temperature as T. For Boyle's temperature we can write it T, in subscript we can put B, or we can state this Boyle temperature. In other words, the temperature, Boyle temperature, is the temperature above which real gas behave like ideal gas, and all the real gas obeys Boyle's law beyond this temperature. So that can be written TB equals to, the value of this Boyle temperature can be given by TB equals to A upon R into B, where A and B are van der Waals constant. We will see in our next lecture. So now this is time. We have already recalled our previous lectures, equations and relations. Now we will apply all of these into the numerical problems. So let us start with the first numerical problem. What is that? Calculate the number of molecules in 1 cc of oxygen at normal temperature and pressure conditions using the following data. What is given? One thing is given, the volume, that is 1 cc. Second thing is density of mercury is given, 13.6 gram per cc. The RMS velocity of oxygen molecule is also given, that is 4.62 into 10 to the power 4 centimeter per second. And the last thing was given is mass of one molecule of oxygen, that is equal to 52.8 into 10 to the power minus 24 gram. So what we have to calculate? We have to calculate the number of molecules. We know the formula, since we know the density, we know the velocity, we know the mass. So we have to apply the formula which contains all of them. Okay, and what is that? That is the pressure exerted by the gas, and is given by P equals to M into N into C square upon 3 into V, right? Now if we rearrange, because we have to calculate number of molecules, so number of molecules is n is given by 3 into P into V upon mc square, right? Now we can calculate the value of P. How to calculate that? We know the formula. P is given by H into D into G, where H is, since we are talking about the pressure, so H is the height of mercury column, right? That is given by 76 centimeter, right? At the atmospheric pressure, it is given by 76, right? It has already given. Why we are using 76? Because it has given at NTP, normal temperature and pressure, and that is 1 atmosphere. So for that, the 76 will be the height of that mercury column. The density is already given 13.6, so 13.6, and the value of G, the constant, that is given by 980. So when we calculate this, we got the value 1012928 dyne per centimeter square. Now if we put, we know the value of P, we know the value of V from here, and sorry, not, this is the volume, so V is 1 cc, so we can write V is equals to 1. M is given here, the mass is 52.8 into 10 to the power minus 24 gram, so we are writing this here, and into C squared. C is the velocity, RMS velocity of the molecule. So RMS velocity is given here 4.62 into 10 power 4 to the power 2, because it is C square. So when we solve this expression, we get the total number of molecule is given by 2.697 into 10 to the power 19. This is our answer for this numerical. Okay, so we have seen how to apply this relation of pressure exerted by the gas molecule. We can calculate any of the variables, any of the values from this equation if the other values are known. The second numerical is at what temperature will oxygen molecules have the same root mean square velocity as that of hydrogen molecules at 100 degree. So there are two different type of molecules, one is oxygen and another one is hydrogen. Okay, now what is asking, what temperature? So one temperature is given, for hydrogen it is 100 degree, for oxygen it is asking, and it is saying the root mean square velocity should be same. That means we can apply the formula. We have already seen the energy of the molecule is given by half mc square equals to 3 by 2 kT, and we can write it for both of the molecules, and that is given by 1 by 2 m1c1 square equals 3 by 2 k into t1. That is for hydrogen molecule. Second is oxygen molecule. Similar way we can write 1 by 2 m2 c2 square equals to 3 by 2 k t2. If we divide these equations, what we will get, 1 by 2 will cancel out, remaining will be m1 c1 square divided by m2 c2 square equals to, here c 3 by 2 into k will be cancelled out, and the remaining term will be t1 upon t2. Now see, we know one temperature, we have to know other temperature. So t1 upon t2 is equals to m1 c1 square divided by m2 c2 square. Right now, because we have considered hydrogen molecule as number one molecule, so that means t1 we already know, right? We have to calculate t2. So take it out the other side. t2 will equal to t1 into m2 c2 square divided by m1 c1 square. We have written this here. The temperature for oxygen molecule is given by this expression. Here we know now what is given, the same root mean square velocity. That means c1 is given by equal to c2. The second thing is at 100 degrees C, t1 is the absolute temperature of hydrogen molecule. Now it is given in 100 degrees centigrade. We have to convert it into Kelvin. So that means that is given as minus 100 plus 273, it is given by 173 Kelvin. And we know M2 upon M1 equals to 16 because 16, that is the ratio of oxygen divided by hydrogen. So oxygen divided by hydrogen will be 16, right? Now, if we put all these values into this equation, we will get 16 into 173, and that is 2768 Kelvin. If we minus 273, we will get 2495 degree centigrade for oxygen molecule, where it has the same root mean square velocity as that of hydrogen molecule at minus 100 degree. Okay, now the next numerical is calculate the volume occupied by 3.2 gram of oxygen at 76 centimeter of mercury and 27 degree centigrade. So first we will see what is given, what can be calculated easily, and what we have to get finally. The finally is we have to calculate the volume. Okay, before that we know P we can calculate easily. P is equals to, it is already given 76 centimeter of mercury, that means it is normal pressure condition. So that is, we have calculated in the last question also, P is equals to 76 into 13.6 into 980, that is dynes per centimeter square, right? The temperature is given by, see, 27 degrees centigrade. So T is 27 plus 273, that is 300 Kelvin at absolute scale. And we know the gas constant value R is equal to, that you should remember always, because we will use it several times in our calculation. That is constant, universal gas constant, so you should remember the value of this. That is 8.31 into 10 to the power 7 erg per gram mole Kelvin. So we know for the ideal gas, PV equals to RT, we have to calculate the volume. So P is given by RT upon P. If we put these values here, R, T and P, we will get to 24,610 cc per gram mole. Now what is asking? Occupied by 3.2 gram of oxygen. So we will multiply by this because we have calculated this per gram per mole, right? Now the volume of 3.2 gram of oxygen will be 24610 into 3.2 divide by, because it was per mole, O2. O2 means 16 into 2, that is given by 32. So if we divide it, we will get the real volume of 3.2 gram oxygen, that is 2461 cc centimeter cube. Okay, this is the volume of oxygen. Now let us move to the next numerical, that is calculate the van der Waals constant for dry air, given that Tc is equal to 132 Kelvin, Pc equals to 37.2 atmosphere, and R per mole is 82.07 centimeter cube atoms per Kelvin. Here this question is related to van der Waals equation. However, we can consider how to calculate this. Okay, so if we recall our lecture 4, we can know that the critical temperature Tc is given by 8A upon 27 Pr. From here, if we rearrange, we know A upon B equals to 27 into RTc upon 8. So because we have to calculate the van der Waals constant, so we need to rearrange it in a way that we should be on one side. Now from the other critical constant relationship, we know Pc is given by A upon 27 B square. From here we can arrange it, A upon B square equals to 27 Pc, right? If we divide this equation by this equation, A upon B divided by A upon B square, that will give B on the left hand side equals to, you can see 27 will be cancelled out from 27, the remaining term will be RTc upon 8 Pc. Now putting the value of all the things, R is given, Tc is given, Pc is given. Now putting these values, we get 36.41 centimeter cube for B. You know B is the modification for the volume term, so it should have the same dimension as that of volume. So B is given by centimeter cube. Now from this equation we already know A upon B is given by this value. So we are putting this A equals to, or we can write in this equation also. Here I use the second equation, A equals to 27 PC into B square. Putting the value of B here, we get 13.31 into 10 to the power 6 atoms centimeter to the power 6. Okay, this is the next numerical that was based on van der Waals constants. Now let us move to next numerical. And a fresh air is composed of nitrogen, that is 78%, and oxygen O2, that is 21%. That is the normal condition for air surrounded us. Now we have to calculate the RMS speed of nitrogen and oxygen at 20 degrees centigrade. So first thing is given temperature. T is 20 degrees centigrade. We have to calculate, we have to convert it in the absolute scale. Remember here, for temperature we always need to use the absolute scale. So every time it is given in centigrade, we have to convert it into Kelvin. So 20 degrees centigrade equals to 20 plus 273 equals to 293 Kelvin. R we already know is given by 8.314 joule per mole per Kelvin. Right? Now we will calculate one by one. For nitrogen, we know the molar mass of nitrogen, that is 0.0280 kilogram per mole. Now we know the formula. The value of RMS velocity is given by Vrms is equals to under root 3 RT upon M. Putting the values of different terms, R is 8.31 into T is 293 divided by M is 0.028. Final answer is 511 meter per second. That is the RMS velocity of nitrogen molecules, right? Second is for oxygen. Here the molar mass for oxygen is 0.0320 kilogram per mole. Putting this value instead of 0.0280, we get RMS velocity of oxygen is 478 meter per second. Okay. So all these numericals I have tried to prepare these numericals so that it can follow different method, it can follow different equations, so that all the laws related which we have studied in our previous lecture should be clear to you. Okay, now this is the next numerical. A gas is at temperature 80 degrees C and pressure is given as 5 into 10 to the power minus 10 Newton per meter square. So what will be the number of molecules per meter cube? So again we have to check first what is given and what we have to calculate. First thing is given the temperature, that is 80 degrees C. So 80 plus 273 is converted to 353 at absolute temperature scale. And second thing is given pressure, that is 5 into 10 to the power minus 10 Newton per meter square. Okay. Now the next thing we know already that Boltzmann constant K is given by 1.38 into 10 to the power minus 23 joule per Kelvin. Right? This is the Boltzmann constant, and that you should remember always. Right? The next thing is given the volume of gas, that is 1 meter cube. Okay, and finally we have to calculate what is the number of molecules. How we calculate B? B is given molecules per meter cube. So we have to calculate the molecules in 1 meter cube. We know the ideal gas equation. PV is equals to RT, and R is given by N into K. So PV equals to NKT. We can rearrange it. N equals to PV upon KT. Putting the values here. P 5 into 10 to the power minus 10 into V is 1. K is given here 1.38 into 10 to the power minus 23 into 353, what we have calculated. By calculating this mathematical term, we get N is equals to 1.02 into 10 to the power 11. These are the number of molecules per meter cube of this gas at temperature 80 degree. The next numerical is calculate the temperature at which the RMS velocity of a gas triples its value at STP, standard temperature and pressure condition. Temperature at STP, we are considering T1 is equals to 273 Kelvin. This is standard temperature and pressure, and which is 273 Kelvin, that is 0 degrees centigrade. Okay. Now Vrms is given. We are considering Vrms of gas 1 is equals to B. Now RMS velocity of gas triples. That velocity is getting triple. So we are considering this gas triple Vrms2 is given by 3V. First we have considered B, and now because it is tripling, so we are considering that is given by 3V. New temperature at Vrms2 is, we have to calculate, and T2 is also known. Now we know Vrms equals to under root 3RT upon M. That means Vrms is proportional to temperature. We can write in the consideration of this equation Vrms square 1 divided by B square RMS2, that is for gas 2, that is equals to B square upon 3V to the power 2, because we know these values here. So it will give, that is equals to 273 upon T2, because it is given by this equation. The first condition, the temperature is 273 Kelvin, and for the temperature we need to know. So if we solve this equation, we get T2 equals to 273 into 9 into B square. That will cancel out from the B square in the denominator. So the remaining part will be 273 into 9, and the calculating value will be 2457 Kelvin for the numerical. Now the next numerical is, if 10 to the power 20 oxygen molecules per second strike 4 centimeter square of ball at an angle of 30 degrees, like this. So we are considering again, if you assume that you remember, we derived the equation for the pressure exerted by a gas. There we calculated for the box. Now what it is saying, the molecules are striking in this direction, so at 30 degree with the normal. So normal is, according to Boyle, the normal will be like this, and it is striking at an angle 30 degrees. So something like this, the molecules are striking with the balls. Okay, the velocity is giving here when moving at a speed of 2 into 10 to the power 3 meter per second. So now we have to find the pressure exerted on the ball. Mass of one atom is given by 2.672 into 10 to the power minus 27 kilogram. Now let us consider first thing, mass of one O2 molecule is 2 into 2.672 into 10 to the power minus 26, because here the mass of one atom is given. If we consider oxygen molecule, the total mass will be 2 into 2.672 into 10 to the power minus 26 kilogram. Now the total number of molecules is 10 to the power 20. Here it is given. So the mass of 10 to the power 20 O2 molecules will be 20 into this quantity, and that will be equals to 53.44 into 10 to the power minus 7. Right? Now we can calculate the momentum of these molecules. P is given by M into V. We already know the mass, we already know the velocity. 53.44 into 10 to the power minus 7 into velocity is here 2 into 10 to the power 3. So we are putting this value, and finally we are getting 106.88 into 10 to the power minus 4 kilogram meter per second. This is momentum of the molecules. Now one condition is giving that molecules are moving at 30 degree, but we have calculated the expression for the normal striking, right? So we have to calculate the velocity component in the normal direction. So normal direction, if you consider, this value is given already, we have to calculate this value, and the relation between this and this is given by cos value. So the component of momentum normal to wall is at 30 degree is given by 106.88 into 10 to the power minus 4 into cos 30. Okay, the value of cos 30 is given by under root 3 by 2. If we calculate this expression, we will get the final value as 92.55 into 10 to the power minus 4 kilogram meter per second. If we consider what is the pressure? Pressure is nothing but force per unit area. So force is what? The momentum change. We have already calculated this 92.558 into 10 to the power minus 4 divided by area, and area is already given 4 centimeter square. We need to convert it into meter because everything is given here in meter. So for converting it into meter, it will be 4 into 10 to the power minus 4 meter square. So we have put this value 4 into 10 to the power minus 4. So if we solve this, we will get 23.14 Newton per meter square. This is the answer for our numerical. Now, next numerical is related to adiabatic process. What it is saying, what it is asking, during an adiabatic process, the pressure of a mixture of monoatomic and diatomic gases is found to be proportional to the cube of the temperature. We have to find the value of gamma, that means the ratio of molar specific heats. Now we know the adiabatic process has three different relations, right? We know P to the power gamma minus 1 into T to the power gamma equals to constant, or we can write it as P into T to the power gamma divided by 1 minus gamma equals to constant. Now from the question, if we see, the pressure of a mixture of monoatomic and diatomic gases is found to be proportional to the cube of temperature. That means P is directly proportional to T cube. If we rearrange in the same form, what we get? P into T to the power minus 3 equals to constant. If we compare these two equations, what we get? Minus 3 is equal to gamma divided by 1 minus gamma. If we solve it by simple mathematics, we get gamma equals to 3 by 2. So the ratio of molar specific heat is given by 3 by 2 in this condition as asked in numerical 9. Now let us move to the next numerical, which is find the adiabatic exponent gamma. The same thing for the mixture of mu 1 moles of monoatomic gas and mu 2 moles of a diatomic gas at normal temperature. Now we know the specific heat of 1 mole of monoatomic gas Cv is given by 3 by 2 into R. Okay, for mu 1 mole it will become Cv equals to 3 by 2 into mu 1 R, because this is for 1 mole. We have to calculate for mu 1 mole. This one will be 3 by 2 mu 1 R, and Cp will be equals to 5 by 2 mu 1 R. Okay, because Cp minus Cv equals to R, that is given by Mayer's formula. We have already studied, so we can calculate the value of Cp also. Now if we consider for the diatomic gas, this is diatomic gas. For that, for mu 2 mole, for diatomic it is Cv equals to 5 by 2 R. So for mu 2 mole it will be 5 by 2 mu 2 R, and from here we can calculate the value of Cp, that is 7 by 2 mu 2 R. Okay. Now a specific heat of any mixture at constant volume Cv is given by 3 by 2 mu 1 R plus 5 by 2 mu 2 R, because we have to mix them. So we are considering this 3 by 2 mu 1 R plus 5 by 2 mu 2 R. Similarly, we can get the value of Cp for the mixture 5 by 2 mu 1 R plus 7 by 2 mu 2 R. Now if we have to calculate the ratio, adiabatic exponent gamma, and gamma is given by Cp upon Cv. That will, if we solve this, we will get 5 mu 1 plus 7 mu 2 upon 3 mu 1 plus 5 mu 2. This is the expression for the ratio of specific heats at constant pressure and constant volume for a mixture of monoatomic and diatomic gas. Okay. The next question is, given 300 milliliter of a gas at 17 degrees centigrade, what will be its volume at 10 degrees C? So we already know the Charles law. Charles law is giving V is proportional to temperature. if the pressure remains constant. So we will apply this for the two condition, and that will become B1 in B1 is proportional to T1, B2 is proportional to T2. If we divide these, so B1 upon T1 equals to B2 upon T2. If we rearrange, B1 into T2 equals to B2 into T1. Now, if we divide both sides by T1, we will get B2 equals to B1 T2 divided by T1. Now, we know the values. B1 is 300 ml, T2 is 10 degree centigrade. We have to convert it into in Kelvin scale. So 273 plus 10 is 283 Kelvin, and at 17 degree is the T1 temperature. So that will be 290 Kelvin. If we solve this, we get the volume is 292.76 milliliter at 10 degrees. The next numerical is calculate the molar mass of a given gas whose diffusion rate is 2.92 times the diffusion rate of ammonia. So this is related to the Graham's law of diffusion, right? Now we already know the question is giving that the diffusion rate is 2.92 times of ammonia, right? So the ratio of the diffuser, the gas, and the ratio of the ammonia and the given gas will be 1 divided by 2.92. So R1 upon R2 is 1 upon 2.92. Now we know the molar mass of ammonia is 17.0307, and from Graham's law we know R1 upon RT is equals to under root rho 2 upon rho 1. Now if we change it into the mass, it will be mass upon volume, and volume is same for both of them. So that will become M2 upon M1, right? Now if we substitute the value of R1 upon R2, 1 upon 2.92, that will become under root M2 upon M1. We already know 17.0307. We calculate this and we get M2 is equals to 2 gram per mole. That is the molar mass of the given gas. Okay, is it clear? Now the next numerical, find the relative diffusion rate of water. The molar mass is given as 18.0152 as compared to hard water, and the molar mass of hard water is slightly different. That is given by 20.0276. Now this is again related to the Graham's law of diffusion. Here the molar mass of water M1 we can consider, that is given this. M2 is given 20.0276. Now let us assume the rate of diffusion of heavy water as 1 because it has slower diffusion rate. So we are assuming it as 1. Now R2 is 1. According to the Graham's law, we know R1 upon RT, R2 is equals to under root M2 upon M1. If we solve this, we get R1 equals to 1.05, and that is the relative diffusion rate is 1.05. If we are considering it as 1, this will be the 1.05. Okay, this is the numerical 13. Now let us move to the last numerical of today's lecture, that is calculate the values of molar heat capacity Cv and Cp of a gas if the ratio of capacities is 1.33. What will be the atomicity of the gas? The given value of R is 8.31 joule per mole Kelvin, right? Now we know from the Mayer equation Cp minus Cv is given by R, and we also know that Cp upon Cv, the ratio of molar specific heat is given by gamma, and that is given by 1.33, right? Now if we solve from this equation, we get Cp is equals to gamma into Cv. Putting this value in this equation, so gamma into Cv minus Cv equals to R. That means Cv is equals to R upon gamma minus 1. So the value of Cv, when we put the value of R here and gamma here, we will get Cv value as 25.18 joule per mole Kelvin. From this equation, by putting the value of Cv in this equation, we can calculate the value of Cp, or even from here also we can get the value. I applied this equation here, Cp equals to 1.33 into Cv, and Cv we have already calculated. So the value of Cp will be 33.49 joule per mole Kelvin. Right now, what will be the atomicity? Atomicity will be directly proportional, directly equals to the number of degree of freedom. Okay, when we studied the degree of freedom, we have considered different atomicity: monoatomic, diatomic, triatomic. So we already considered, if we are considering only translational motion, okay, in this case only translational motion. So in that consideration, the atomicity will be equals to the number of degree of freedom, and number of degree of freedom is given by 2 upon gamma minus 1. This is given from the formula of the relation between molar specific heat and degree of freedom. So the equation is F equals to 2 upon gamma minus 1 and 2 upon 1.33 minus 1, that is equals to, almost equals to 6. So the total number of degree of freedom will be 6. That means the gas is polyatomic. If it is monoatomic, it will be 0. But if it will be diatomic, the degree of freedom is 3. If it is polyatomic, then only the degree of freedom can be more than 3, right? So the gas is polyatomic. Okay, so this is all for today's lecture. I hope the laws which we have already studied must have been clear to you by solving these numericals. I hope this lecture is quite useful for you to solve these numerical problems by yourself. You can practice at your home, you can practice everything, and in the next lecture we will consider the other theories, such as we have already studied about the this is van der Waals equation of state, the modified equation of state, and several transport phenomena of gases, that was viscosity, diffusion, and the thermal conductivity, right? So we will consider it in our next lecture. Okay, thank you for your attention, thank you for listening, thank you for your patience.